Hi everyone, my name is Sriharsha. I work as a data scientist at Condé Nast Technology Labs. Today I'm going to talk on building recommendation systems using graph neural networks. My agenda is simple. First, I wanted to discuss what are the graph neural networks, and we will see how are we using graph neural networks within our company. So coming to the graph machine learning, it's just a branch of machine learning that deals with the graph data. So whenever we talk about a graph typically consists of nodes and edges. And along with the nodes connecting to each other, nodes can also have some feature vectors associated with them. Even the edges can also have the feature vectors attached to them in some cases. So graphs come in different kinds. For example, if you consider the Facebook network, so the friendship relation is actually a bidirectional. And if you consider the Twitter follow relation, you can follow someone in the Twitter, but it's not necessary that they should follow you back. So it's a directed edges. And also the graphs can have self edges, and the graphs can be homogeneous and heterogeneous. So when I say homogeneous, all the nodes and relations in the graph are of same type. And when we say heterogeneous, the nodes can be of different types in the graph, and also there can be multiple edges between these nodes. There is an other classification into this called multi-graphs. I can give you an example on this. Consider we have an employee and the location. So one relation between employee and location is that employee lives in a particular location is one relation, and employee works at a location is another relation. So when there are multiple relations between two different kinds of entities, we call it as a multi-graph. So given that introduction, coming to the graph neural networks, so these are also a family of neural networks that learn an embedding for a node or an edge or for an entire graph. So for example, if you look at this network here, if you wanted to learn a representation for this target node, so we typically consider this target node's neighborhood. So we can go any hops away from that node. So if you observe this diagram, so from the target node, you can go one hop away from it, which are all these green color nodes, and you can go two hops away from it, which are all these blue color nodes. So we typically wanted to consider all the neighborhood nodes of a target node to update its representation. Let's see how are we going to do. So this is the crux of the graph neural networks. There's a concept called message passing, a neural message passing. So here the goal is to obtain the neighborhood aware embeddings. So you can consider this example here. So the messages are sent between the nodes via the edges. So let's assume the purple color node that we have here is our target node, and there are four neighbors attached to this specific node. So as a first step, it will collect the messages from its neighbors. Then it will follow some aggregation rules to aggregate all these messages and then update itself. So this process is repeated in parallel for all the nodes in the graph. First, they'll collect their neighborhood messages, aggregate their messages, and update their own representation. So the new representation will take into account the neighborhood of a node as well as its previous state. Let's see mathematically how we explain this concept. So like I was saying, we have three functions. The first function is a message function. So message function is a combination of the source node's own representation and the neighborhood's representation and the edges representation if we have any. So here, just to explain the notation, I'm calling I as a source node, J as the destination or the neighborhood node, and K is a message passing step or a graph neural network layer number. So a message function can typically a combination of these three things: the source node's representation, the destination node's representation, and the edge representation. So one of the examples that we can define is a simple neighborhood copy. You know, we can only consider the node's neighborhood information as a message function. So that's what I was referring here. So m subscript ij is equal to h subscript j. So this is nothing but the message that you receive from J is nothing but the jth node representation. So the neighborhood copy is a simple message function. Coming to the next function, this is a aggregate function. Okay, let's assume in the same example, let's assume the purple color node is the target node. Let's say you have collected all the messages from its neighborhood. So you receive 4 different messages from 4 neighbors. So now the next step is to aggregate these 4 neighbor messages. So there could be different things that are that we can formulate, but one of the easiest way to aggregate these neighborhood vectors is to simply take a summation. You know, you get the neighborhood vector representations. You just sum up all these whatever neighborhood vectors you have for that given node. That is an aggregated representation. So there are 2 rules for the aggregation function. So the first rule is the fixed length representation. You know, uh, for any given node, the neighborhood size can vary. For one node, there could be 3 neighbors. For another node, there could be 10 neighbors. But in both of these cases, we want a single vector that should represent the node's neighborhood. And the second rule is the permutation invariance. You know, in graphs, the nodes comes in arbitrary order. There is no inherent order we can define on the nodes. So it's the same way as like, for example, if you take the summation operation, if you add 3 numbers, let's say 1 plus 2 plus 3, let's say you add them in a different order, like 2 plus 3 plus 1. So in both of these cases, you're going to get the result as 6. So irrespective of the order of the values, you're getting the same output. That is what we want here also. Irrespective of the node's neighborhood order, we wanted to have the same output. So you pass, let's say, node 1, node 2, node 3, or in a different permutation order, node 3, node 1, node 2. The final result should be same for any of these arbitrary orders. So one such example is simply take a summation. So you get all the messages, you just sum up all these vectors. Hence, you'll get a single fixed length vector representation, which you can call as aggregated representation, which I'm referring here with the notation mi hat. So I is our source node. So there is a neighborhood around this I. So you get all the messages and then aggregate, and you refer it to mi hat. So now we have the messages, and then we aggregated those messages. So now the next important step is to update. Okay, you have the messages, you aggregated the messages. So now how do you use this aggregated representation to update yourself? So again, this function is a combination of the node's initial representation, which I'm referring as h subscript I, and also the node's neighborhood representation, which I'm referring as mi hat. So one of the examples is we can simply concatenate the source node's initial representation and the source node's neighborhood representation, and we can do a simple linear projection on this. So when I say linear projection, it's nothing but a fully connected linear layer in neural network. So at the end of this update step, the node should not only know about itself, but its neighbors as well. Okay. So given that these 3 functions, so here is a small example using the deep graph library. So this is how a single graph neural network looks in PyTorch or in DZL. So we have message passing APIs that are built in DZL, which are very easy to use. So you have a pre-built functions for messages, aggregators, and updates. So you have this message passing API called update underscore all. So whatever you give within this function will be applied for for the entire graph. So here I'm just defining the examples that I have shown before. For the message function, I'm using a neighborhood copy function. For the reduce or aggregate function, I'm simply summing up the neighborhood vectors. And if you see closely here, so once you get an aggregated vector, so I'm concatenating the node's own representation and the node's neighborhood representation, and that concatenated vector is what being passed as an input to the linear layer. That's why here on the line 13, I'm putting it as like input features into 2. because we have node's own representation and node's neighborhood representation. Concatenating both together will give you will multiply the dimensions by 2. Okay, and also another important point here is that uh, you know uh, the number of layers in the graph neural network represents how many hops can we go away from that node. Okay, so this is how a simple graph neural network looks like. So now coming back to our product, so we call it as RECON, which is an acronym for recommendations using knowledge networks. So RECON is a machine learning project that is centered around improving our user and content-based intelligence. And also we want to use RECON to provide better personalized recommendations, and also to provide better entity representations that can be used in the other downstream tasks. So we represent the dataset of our site interactions as a heterogeneous graph. So when I say heterogeneous, I can have multiple types of nodes and multiple types of relations. So we are considering users, articles, authors, and our user demographics as entities. And the edges are simply the interactions between each of these nodes. Just to show you the schema, so this is how our graph looks like. So we have our user or our subscriber, and we know what are the articles that the user has interacted in the past. So that will be a relation between user and a given article. And we also know who are the authors that are written these articles. And we also have some demographic information like the metropolitan statistical area, the income range, gender, household, age group, and all these are encoded. All these, all these demographics are encoded. So this is what we have. And at every node, we also maintain some node features. For articles, we maintain the 100-dimensional doc2 vector embedding. But for the other nodes, such as users, demographics, and author, we only maintain a random 100-dimensional embedding. Okay. So right now we are using Recon in the newsletter personalization use case. So in our newsletter recommendation problem, the task is to populate emails sent out to opt-in subscribers with recently published content. Typically, each newsletter in Condé Nast consists of 6 recommendations. The newsletter is emailed directly to the subscribers who opted in. We receive information related to their interactions with this email. Did they open the email, or how many articles did they click from the email, so on. Our primary metric is the CTR. So that is the probability that a user will click on at least 1 out of 6 recommendations given that they have opened the newsletter in the first place. So we only calculate this CTR for the open newsletters, not for all the sent newsletters, only for the open newsletters. So we kind of posed this recommendation problem as a link prediction problem, such that we can leverage the graphs. So when you ask like what is link prediction, so given a snapshot of network at a time t, identify pairs of nodes that will either form a link or not in the future. Given the past user and article interactions, can we predict what are the articles that the user might like in future at some future time interval, like let's say at some future time step t dash. And coming to the link classification, if you think in general, it's very unlikely that every user reads every article. So if you think from this simple bipartite graph point of view, if every user reads and every article, so that should be the maximum number of possible edges in the graph. But in any use case, that should never be the case. We only have a small, a subset of the total number of possible edges. So I'm referring here with a Venn diagram. So if you consider this big circle as the total number of edges, that is when every user reads every article, but that is not the case. We only have a small subset of this, which I'm referring to this green circle. So we are referring the original interactions between user and articles as our positive samples, and we generate some negative samples. That is nothing but we create some fake edges in the graph. So we create some fake edges between the users and articles. So that will be our negative samples. So now we have the positives, which are nothing but the users' past interactions. And we have also sampled the negative ones from the total number of possible edges, which can act as our negative sample set. So now as we have positives and negatives, it looks like a simple binary classification. So we kind of posed the link prediction problem as a binary link classification problem. So again, you might think, okay, we have the user demographics. So why do we creating these nodes as different entities? Why can't we have this information as the user attributes, as the node features? The reason that we choose this design is to solve the cold start problem. Especially in our use case, we have a major proportion of user without any interactions. So we wanted to handle them as well. We wanted to provide recommendations for the new users as well, are the users without any interactions. So if we assume the case where we don't have the demographics, then all these users will be isolated in the graph. You can't really aggregate the neighborhood around that node because there is no neighborhood at all. But having these demographics in place, we can have some neighborhood around the node. If not some real recommendations, at least we can make the recommendations based on the demographics. If you observe this example here, we have a user one here. Okay, so user one is reading article 3, and similarly you have a user 2 here who is reading article 1. So if you compare user 1 and user 2, okay, they are two separate users. They're like completely two separate users who are reading different articles, but they still have some connection on one of the demographic entities called a metropolitan statistical area. So you can assume a case where the user don't have an interaction at all. In that case, still the message from this user is being propagated into user 2 through the neural message passing. So this was the main idea. So even though the users don't have any interactions to the articles, still we can learn some good representations depending on the neighborhood of the demographic nodes. And also for every article, we are having the author node as a different entity, but not as a node feature. Again, here also the same reason. We wanted to recommend the newly published article which have a minimal views or which have no views at all. The same case. So having the demographics and authors as separate entities, helps us in making recommendations for the cold start users and the cold start articles. And at a high level, so this is how our pipeline looks like. We typically update our data sets on the user article activities, articles information, authors information, demographics information, and the embeddings are the initial node vectors for every node. And we also have an integer ID lookup because we use a library called a deep graph library, which only accepts the integer IDs for the nodes. So hence we maintain a lookup table for the string IDs that we have and the integer IDs that we feed into the graph. So we process all these different data sets and convert everything to be of the form nodes and edges, such that we can feed this data into a DZL graph object. So using the nodes and edges, we create this graph of users, articles, authors, and demographics. We save the graph in S3 with an extension .dcl. We use the graph to train the model and validate. So once we train the model, we log the model using MLflow in Databricks. And after training the model, after saving the model, the next step is to generate the candidates. So when I say candidates, it's nothing but the pairs of users and articles for your recommendation. So typically in our newsletter recommendation use case, the candidate set of articles will be the subscribers who have opted in for the newsletter, and the candidate set of articles are the recently published articles. So we kind of wanted to predict the link between the subscribers and the articles that were published very recently. So what we do is that we generate the candidates and we save the candidates in S3. So now if you look carefully, now we have a graph which we have created at the beginning. We also have a model which we have already trained. We also have the candidates that we have generated here. So now we have three inputs. We have a graph, we have a model, we have the candidates. So we pass in all these three inputs into scoring module to predict the links between user and article. So we use the graph that we have here for the neural message passing. That is to get the representations for every user, article, and every other nodes. And we use the trained model to make inferences. And then we use the bipartite graph of users and articles for which we wanted to predict the links for. So at the end of the scoring, for every candidate pair, you get a score, you get some score. So let's assume, we have a million users. Let's say we have a few hundreds of articles. So now you get the scores for all these pairs of users and articles. Then we do some post processing, where we re-rank the articles and exclude the ones that the user has already seen. And after doing all the post processing, for every user, we'll get the 6 articles that the user might be interested in. So we deploy this using sail through in our into our emails. So this is a high level pipeline that we have for Recon. And most of the things were set up in Databricks. Yeah. So coming to the model architecture, so we were using a 2-layer encoder and a simple decoder, which can be a multi-layer perceptron. So coming to this architecture, if you look closely, so it's a simple architecture. So the 2 layers in an encoder refers to how many hops away from a node can we go from. And if you look carefully, we have a heterogeneous graph. That means we have multiple relations. We have a relation between user and article. We have a relationship between article and author. We have a relationship between user and different demographics. So you can assume the same architecture. We were using the same encoder for all the relations. So how we do this is like, instead of having a single encoder for the entire graph, we kind of stack up different encoders where each encoder is responsible to learn each relation. So you can assume this is an encoder to learn the relation between users and articles. There will be a different encoder which will learn the relationship between articles and authors. There will be a different encoder which will learn the relationship between users and demographics. So we kind of stack up all these encoders, and there is a way to aggregate the outputs from each of these encoders. So that's how you should look at it. Even though for the demonstration purpose, I'm putting it as a single encoder. Typically, you should assume that the number of encoders will be equivalent to the number of relations in your graph. And the decoder is a simple, it can be a single multi-layer perceptron or a simple dot product or a single layer perceptron, whatever works for your use case. So if you look the code for this, it's pretty simple. So you define the encoder where I'm using the graph neural network class, which I have defined before. And I'm also defining the decoder. So the decoder's job is only, to collect the embeddings from the encoder and then predict the link between user and article. So just to explain the same thing, so the output of an encoder is the node's representation. Okay, for every node you get a representation. So let's say you wanted to find the link between two different nodes. Let's say you wanted to find the link between user node and an article node. So now from the encoder, now you have a representation for all the users and all the articles. So you can simply concatenate the user's representation and the article's representation, and you can pass this concatenate vector as an input to a fully connected layer. So it's like a simple, binary classification. You give the user representation, article representation, and ask the multi-layer perceptron to give you a prediction. What is the probability of this link being present in the graph? So this is a simple example. I have just put here some sample, some sample numbers just for the familiarity. You can have a look at it. And just a few things on the scoring. The architecture that we have produces a score for any given hypothetical edge. So in order to turn that into recommendation, we score a candidate set of user article edges only. Because our graph contains users, articles, authors, and demographics, typically we can use this architecture to predict any of these relations But given our problem or our use case, we were only trying to predict the links between users and articles. The candidate generation process also can be chosen or modified, based off of our priorities. The current strategy that we follow for a few brands is only to consider the articles that were published in the very recent past. So that is about the recurrent scoring. Thank you. Feel free to drop any questions that you have. Cool.